So in this video, we're going to actually write the code for our function. One thing that I wanted to show you is that, and I'm going to kind of walk you through step by step, we're going to make a modification to the function. But really, the key point that you want to realize is if you ask yourself, what do I actually have to turn in from this? What kind of screenshots am I pasting? It seems like he did the whole thing for us. That is exactly the case. I did do the whole thing for you here. And I know it's because we're only in the second lab. I find it effective to kind of initially teach people how to code by showing them step by step what to do, and then giving them tasks where I take the code that I handed them, I show them how to code it in real time. That way they understand the logic and motivation behind what I did. And then we're going to have some assignments down the road where we're going to take some of these functions and I'm going to ask you to make modifications to them. And that's actually going to be the case here, as you'll see once we get through the video. So what I'd like you to do now, if you look at what our deliverables are, we actually want to take and copy the code of the function that we're going to write. It's going to be the function that we described in this block diagram and pseudocode here. And then we're going to show a screenshot just showing me that you went step by step with me and actually validated your code. So the first thing you need to do is open MATLAB, and we're going to write a new function. So we need the text editor integrated within the integrated development environment of this application. We're going to get it by clicking on the new button, but don't just click new because that will only create a new script. Left click on the downward arrow here and go to new function. And the reason you want to do that is that will not only open the text editor, but it will have the syntax required to write a function pre-populated for you. And if you look here and remember back to our lecture, a function has a header, keyword function, vector of the output arguments. They can be anything from 0 to however many you want, typically in practice limited to somewhere between 5 or 10. We're going to assign this output vector using the equal assignment operator. This is the name of our function. It has to be a syntactically valid name, meaning that it starts with a letter, contains only letters, numbers, and underscores, and it should be useful. It should be descriptive of what the function is doing. And then within parentheses here, we're going to pass in the variable names of our input arguments. So the way that we're going to write our code is to go to the actual documentation that we have here. Notice that we need 3 inputs, the source voltage, the resistance, and capacitance. We can pick valid variable names for those. I'll just call them VS. R, and C. We chose to actually name our function, and maybe you chose something else. Compute RC current written in camel case. I'll put it here. Compute RC current. We are going to produce an output of just the current. I'll call it capital I, even though for those of you that have taken an engineering class before, you know that really this should be lowercase I because it's a time varying current. The reason I'm not doing that, sorry, I have some stuff in my workspace that I'm going to clear, is if I look at MATLAB actually recognizes lowercase I as the complex unit. So it's not good. I mean, you can kind of overlap and define a variable I, and we'll get into that entire concept of scope and aliasing later on in the course. But for now, let's just avoid it and let's use capital I. So I have my keyword function. I have the name that I've picked for my particular output variable. I have this assignment operator, the name I picked for my function, and all of my input values. And if you know MATLAB, notice MATLAB's going crazy on the top. It's saying, hey, each of those input values, you're not actually using them. And hey, this value you want to return, you're not actually defining it. And that's okay. We'll get to that in a minute. Now that we have our header filled out, I'm going to Control S to save. Notice that by default, MATLAB will want to call it the name of the function. That's good. Click Save. Notice that now it's in your actual MATLAB drive in your current directory. Now, what I'd like you to do, before I change anything else, actually just type help and then type the name of your function and then execute that command. Where have you seen this text before? Untitled 2, summary of the function goes here, detailed explanation goes here. That's actually in these comments that are pre-populated directly beneath the name, the actual function header. So what you want to do is actually change this. I'm not going to have a detailed explanation, but usually what you do, if you remember untitled 2 was the name of the function. So I'm going to copy the name of the function that I picked, and I'm just going to write a brief summary of what this does. And I'll say this function computes current, and then I'll, in parentheses afterwards, say the name of the actual variable I in an RC circuit for given DC voltage, VS, resistance R, and capacitance values C. So it doesn't, this isn't actually being interpreted by the MATLAB interpreter. It's just for you and other end users that use your functions. Remember, when you write functions, it's probably going to be used by both yourself later on in a repeated fashion, maybe way down the road when you don't remember exactly what it does, along with other people that don't want to dive into the details of your code. They just want to know, hey, what did I put in? What did I get out? So these comments are actually probably the most important text within your actual code here, assuming that the code works, of course. So now notice if I re-execute help with the name of my function, I see this description that I actually just typed in. So that's wonderful. So how am I going to actually do this next? Well, if I were you, I would take and I would make a comment for each line of my pseudocode. So if you go back to your pseudocode, we need to actually define tau. We need to define the spacing for our actual array. We need to define the time array, and then we need to compute the current. So let's talk about how we do that. So I'm just going to make all the little comments here. I'm going to say define tau equals r times c, and then I'll say define the spacing for my time array, and then I will define my time array, and then I'll compute my current. So how am I going to do this? Well, we have to pick a variable name for tau, right? And since we can't write Greek letters in our actual code, I'm just going to use the way that it sounds, TAU. And remember that the software already knows what R and C are. It knows that it's inputs to our function. It's telling us up here in the integrated development environment that we're not actually using R and C. So what I'm going to do is I'm going to create a new variable tau that is a valid syntax name. I'm going to assign its value the product of R times C, which are functions that are being passed in. I'm going to terminate this computation with a semicolon, because when the end user runs my function, he or she doesn't want to see the value of tau. He wants just the value of I passed back. After I've done that, I need to define the spacing for my time array. I have to pick a name for that. I'm going to call it delta t, since I'm going to call my actual time array t. Helps to spell it right there, so delta t. And if you recall back to the argument that I did in the first video, it makes sense to set this as a function of your actual value of tau, since that's how long you're actually going to compute your current for. So I'm going to say that delta t is going to be equal to tau divided by 10. So that's going to give me 10 samples per time constant. So usually I will write in a comment why I picked that specific value. And usually if I were coding this, I wouldn't actually have a 10 there. I'd have number of samples per time constant as a variable. That way, if I ever use that again, I would only have to modify one line, and it would make my code more readable. So the way that I'm going to define my time array is I'm going to pick the variable that I'm going to use to store my time vector. I'll call that t. I'll use colon notation, and I'll actually start, and I'm going to zoom in just a little bit because I know when I post these to YouTube, it can be a little bit hard to read. But I'll pick the variable for my time vector t. I'll assign it the values of. I'm going to use colon notation. I need to put the start, colon, the step, colon, the stop. So I'm going to go from 0 up by delta t all the way to 5 times the time constant. And then I'm going to actually make the computation for my current. And if you look at the actual pseudocode that we have here, right, remember that it's computed as V of S divided by R, scaling an exponential decay function. So I have the values of VS and R. Those are being passed into my actual function. So I'm going to call, remember we've already committed to the name of the output variable that we're returning, I. So I'll say that I is equal to VS divided by R times, now question for you, how do you actually get this exponential base function, E here? Well, in most programming languages, that is built in, and it is going to be called exp. Now, what do I want to pass in? Well, I have minus t, and then I want to divide by tau. And what you're asking yourself, well, where did he get that formula from? That's just the underlying physics that govern the physics that govern the underlying first order RC circuits, their transient responses. And it's what we actually want to build up a customized function to give someone the ability to compute what this current looks like for, and remember, it's always exponential decay, to 0 and about 5 time constants with a max value of VS divided by R. And that's what we're trying to build for someone. So we will call this I. And if you look at the equals here, it's telling, hey, you probably want a semicolon. You don't want to spit out all of that information for the end user. So I'm going to terminate that with a semicolon. I'm going to save it. I'm going to scroll up and down my file. I don't see any red underlines. That means that it's free from syntax errors. You can always click this refractor button in MATLAB, or there's usually, let me see actually here, Smart Index. Don't worry about the refactor for now. But usually if you highlight all this and then you hit Smart Indent, usually that will make your code a little bit prettier. It is not doing it for us, but there's really no need to do any indenting here. So I wonder why that didn't work. Anyways, we'll deal with that issue later on in the course when we talk. Really, you don't have to worry about indenting until you get to kind of nested loops within your code. Then it just helps with readability. Indenting doesn't actually influence in languages like MATLAB how the actual code is executed. It's really just about formatting to make it more readable for you. So we have our function here, at least doesn't have any syntax errors. Now we want to validate it. And usually the validation process, you pick particular values on the command line of your input, and you just see, hey, A, does it run? And B, does it produce something that looks like it should? So I'm going to define a variable to store what my function is going to produce. I'm going to assign it equal to, I'll type the name of my function, and then I'll pass in just some values. So say I pass in 1 volt source, a 10 to the third, and maybe I'll, just to make it more readable, I'll put 1 times 10 to the third. That's going to be a 1 kilo ohm resistor. And then for the capacitor, I'll pass in a 1 microfarad, 1 times 10 to the negative 6. So if you've had a physics class or a circuits class before, you might have seen component values like this. If you don't understand what they mean, just remember that this function, all that it does is it decays to 0 from this maximum value, which is V of S divided by R, in about 5 time constants. And the way that you compute the time constant is simply the product of, we have it up here, R times C. So if you multiply these two specific values that we picked of R and C, 10 to the third times 10 to the negative 6 is going to be 10 to the minus third. So I can just hit enter here. I notice that there's a value of vector I in my workspace now. It is 51 units long. If you think about what we just said here, remember that the actual time constant here is going to be a millisecond, or 10 to the minus third. If I want to plot in general, whatever the time constant is, if there are 10 per period and there's 5 of them, you're going to get about 50. This is an off by 1 thing that results from the way of using the colon notation, but don't worry about that for now. All that we've shown, though, is that this executes without any syntax errors. It would probably be good to visualize that resulting vector that we got and see whether or not it produces something that's physically meaningful. And the way that I can do that is with the plot command. So if I plot that vector that I just produced by my function and I hit enter, notice that I get an exponential decay curve, as I would expect. And I, of course, could make this prettier. I could label it and whatnot, but really all that I was testing to see was that my function worked. And this is by no means an actual exhaustive validation here. Really, I would like to get into more details. And one thing I wanted you to think about too. So this is the screenshot I actually want for your lab. But if you were really to think about ways that you can improve this function, how would you do it? So if you notice here, you're plotting I on the y-axis, but what is the x-axis? Well, the x-axis is just like an index count of the element in the vector. So if you notice, the x-axis here is just ranging from 0 up to 51, right? So all that it's doing is it's telling you, hey, the first value of that vector is this much. The second value is this much. The third value is this much. So what you might see when you get here in the actual real world is, man, I probably should have returned the time value as well to allow someone to make that plot. So we're not going to do it here just because this lab is getting long, but think about how so take a screenshot of this, turn it in here, right there, copy all your code there, but ask yourself, how would I modify this function in order to also return someone the time vector for which this actual current is defined? And it's actually only 2 keystrokes. Just go up here to the list of outputs that you're returning, and rather than just return I, also return T, which is already computed here. Hit save, right? And then all that you need to do is now when you call your actual function, rather than just grabbing the value of I, also grab the value of T. And then now when you run that, notice that T is returned in your workspace as well, along with I. And you can make a plot of I versus T now using this type of notation. And then this is actually interpretable because this x-axis is in this case, units of seconds. Notice that it's scaled by 10 to the negative third, so it's really milliseconds. We computed the time constant of 10 to the negative third, which is 1 millisecond. We said this thing dies out after 1, 2, 3, 4, 5 time constants. So this is actually the perfect validation screenshot. But again, I don't want you to think like that, oh, you have to make this modification. I'm actually, now that I think about it, I'm going to modify the Word document a little bit and actually explicitly ask you what modification we made in order to make this function more usable. And that we'll end up using it for the actual rest of the lab. So this is what you get when you have someone that's making new assignments kind of on demand during the semester. But that either whether you include the first screenshot or the second screenshot, that's totally fine. Again, the point of this lab is to kind of just get you in the habit of seeing how you actually write functions in MATLAB, how you go through a basic validation process, and more broadly, how you break up workflows into scripts and functions.